Without warning, something extraordinary entered the solar system, silent, swift, and unlike anything seen before. It arrived unannounced, cutting through space at an unprecedented velocity. By the time humanity's telescopes caught sight of it, the object was already on its way out, slipping back into the interstellar dark. Astronomers around the globe rushed to gather data, to make sense of a fleeting enigma. But time was cruelly short, and the observations they managed to collect only deepened the mystery. This intruder didn't behave like anything familiar. Its motion defied expectations. It accelerated when it should have decelerated, veered in ways that no known comet or asteroid should. Some dismissed it as an unusually shaped rock, while others quietly speculated that it could be something far more profound. In the end, it offered more questions than answers, and now, as it fades into the vast expanse between stars, uncertainty remains. What exactly came through the solar system that day? And did humanity fail to recognize the most significant visitor it has ever known? The object was first spotted in mid-October 2017 by a telescope perched atop a Hawaiian mountain. Initially, it seemed ordinary, a small object gliding across the sky, perhaps an asteroid or a comet as routinely seen by astronomers, but its behavior quickly shattered those assumptions. Unlike the countless celestial bodies that are bound by the sun's gravity, tracing predictable elliptical paths, this object was clearly unbound. It wasn't orbiting anything. It was on a hyperbolic trajectory, speeding through on a one-time passage. Calculations revealed its origin lay far beyond the solar system, possibly from another star or even more distant reaches. The object was given the name Umuam, meaning a messenger from afar arriving first, in Hawaiian. By the time it earned that name, however, it was already vanishing from view. Only a narrow observational window had been available, mere weeks before it grew too distant and faint to track. With barely a fragment of data to work from, scientists raced to decipher its nature. There would be no second opportunity. While initially thought to resemble a comet, Umuam lacked a tail or visible outgassing, even as it passed close to the sun. A rocky asteroid seemed possible, but even that didn't align with the observed properties. It quickly became apparent. This was not just another interstellar rock. Umuam was a puzzle, arriving without warning and leaving before it could be understood. Several aspects made it unlike anything ever observed. Its trajectory was more than just hyperbolic, it was extremely so, suggesting a speed and direction unshaped by the sun's pull or any known gravitational interactions within the solar system. It shot in at a sharp angle, swung past the sun, and departed with even greater velocity. Its shape defied expectations. No telescope captured a direct image, but the pattern of its reflected light offered clues. The brightness fluctuated periodically, rising and falling every few hours in a rhythm that implied it was tumbling through space. The data suggested a highly elongated form, possibly a long, narrow cylinder or a flat disk, each spinning unpredictably. Neither shape matched the usual profiles of natural solar system bodies, which tend to be lumpy, irregular or spherical. Adding to the strangeness, it spun erratically, like a bottle flung into the air, without the stability of natural rotational dynamics. Its surface was uncommonly reflective, shining more brightly than expected for typical rock or ice. Unlike known comets, it emitted no detectable heat. NASA's Spitzer Space Telescope spent 30 hours trying to register any thermal signature and found nothing. But even among all these anomalies, one feature stood out as the most perplexing. As Umuam exited the solar system, it unexpectedly accelerated. This unexplained boost defied conventional physics. There was no visible jet of gas or dust that might indicate cometary outgassing, a mechanism that could account for propulsion. It simply sped up in silence and continued on its course into the cosmic unknown. Typically, when an object from space loops around the sun, its velocity decreases. The sun's immense gravity exerts a pull on all things, subtly stealing their momentum and curving their trajectories. Even the fastest interstellar visitor should not be immune to this cosmic braking. Yet, in the case of Umuam, something defied expectation. After its slingshot past the sun, it didn't slow, it sped up. At first, the acceleration was almost imperceptible. a tiny deviation only precise calculations could catch. But the data was clear. Some unseen force was nudging the object forward, gently but steadily, in defiance of the sun's gravitational grip. It was a phenomenon that left astronomers stunned. The acceleration was real, but its source remained elusive. Under the laws of physics, objects don't just gain speed without a cause. Motion in space is governed by known forces, either internal propulsion or external influences like radiation or gas jets. In the absence of these, trajectories are predictable. But Umuamua's behavior broke that rule. It was as if a stone, tossed up a hill, had decided to keep climbing without being pushed. Initially, many suspected an error. Perhaps the data was flawed or the calculations had overlooked some subtle factor. Yet after repeated analysis and the elimination of known variables, the anomaly stood firm. The object was accelerating as it departed the inner solar system, and no conventional explanation seemed to fit. One leading hypothesis considered the pressure of sunlight. Photons, though massless, can exert force, an effect used in solar sail technology. If Umuamua were extraordinarily light and thin, such as a wide reflective sheet, this might explain the acceleration, but observations contradicted that. The object's rotation was erratic, its reflectivity inconsistent, and its thermal signature lacking. Another possibility was comet-like behavior. In comets, sublimating ice can produce gas jets that push against their surface, altering motion. These jets also form the visible tails and glowing comas so characteristic of active comets. If Umuamua were releasing gas even faintly, it might account for the extra push. Yet not a trace of this activity was found. Sensitive instruments, including the Spitzer Space Telescope, scoured the object for heat or gas emissions and came up empty. There was no tail, no coma, no dust, no sign of venting at all. This absence of evidence left the scientific community with two uncomfortable conclusions. Either an unknown natural mechanism was at work, something never before witnessed, or the object was not entirely natural. Both options challenged long-held assumptions. Science thrives on explanation, on patterns that can be measured, tested and repeated, but Umuamua slipped through that net, raising questions that no existing theory could fully answer. Worse still, time was not on their side. As the object raced away from the sun, it became increasingly unreachable. There would be no second look, no follow-up mission. All that remained were a handful of observations, fragmented data, and a cascade of competing theories. In that vacuum of certainty, more speculative ideas began to surface, ideas that made many scientists uneasy. Because when known physics fails to explain a phenomenon, the door opens to possibilities that are stranger, more controversial, and sometimes profoundly unsettling. When unusual phenomena occur in space, science typically turns to well-established principles for answers. Gravity to explain odd orbits, outgassing to justify unexplained acceleration. But in rare cases, familiar models fall short. That's what happened when Umuamua, an object from outside the solar system, passed through in 2017. While the scientific community largely scrambled to align its behavior with known natural causes, one voice diverged from the crowd, that of Harvard astrophysicist Avi Loeb. Loeb is far from a fringe thinker. A distinguished scholar with hundreds of peer-reviewed publications and decades of academic credibility, he brought mainstream expertise to a highly unorthodox idea. Rather than forcing the object into a traditional category, asteroid, comet or rock, he raised a question few dared to pose. What if Umuamua wasn't natural at all? The observational data offered reasons to be skeptical of conventional explanations. Umuamua's acceleration lacked any visible emission of gas or dust. No coma, no tail, nothing that would typically accompany a comet. It was smaller than expected but highly reflective, and its trajectory didn't align with predictions based on gravity alone. Light curve analysis hinted at an extreme, possibly flat geometry, nothing like the rounded shapes common among known solar system objects. In response to this puzzle, Loeb proposed a radical but scientifically grounded possibility. Umuamua might be artificial. Specifically, he suggested it could be a light sail, a paper-thin structure capable of being propelled by the gentle push of solar radiation. He supported this claim with calculations, showing that a structure mere fractions of a millimetre thick could achieve the observed motion without requiring gas jets or hidden outgassing mechanisms. It was an idea rooted in physics, not fantasy. The scientific community's reaction ranged from outright dismissal to cautious intrigue. Critics argued that such an extraordinary claim demanded extraordinary evidence. More reserved voices acknowledged the elegance of Loeb's theory, while insisting natural explanations be thoroughly exhausted first. Ideas like exotic ices or hydrogen icebergs gained traction, but each came with critical flaws. Hydrogen, for example, is too volatile to have survived an interstellar journey intact. Other candidates, like nitrogen sheets or dusty composites, failed to fully align with the object's peculiar characteristics. Undeterred, Loeb continued to press the question. He published articles, gave interviews, and authored a book challenging what he saw as a cultural issue within science itself. He argued that science should remain a conversation with nature, not a fortress built on rigid presumptions. When evidence defies expectations, it should prompt deeper inquiry, not quick dismissal. To expand the search for extraterrestrial technology, Loeb launched the Galileo Project. Unlike traditional efforts like SETI, which focus on detecting radio signals, this initiative aims to find tangible artifacts, fragments, satellites, or unidentified aerial phenomena that may offer physical proof of non-human intelligence. The goal isn't to chase science fiction, but to apply rigorous scientific methods to questions many fear to ask. Underlying Loeb's argument is a broader philosophical stance. The universe is too vast and life too resilient for humanity to assume it stands alone. If intelligent civilizations exist elsewhere, it's not unreasonable to consider that one of them might have noticed Earth or left behind something that passed nearby. He never claimed with certainty that Umuam was alien in origin. He simply insisted that it could be, and that ignoring that possibility would be a failure not only of science, but of imagination. Whether future evidence supports his hypothesis or not, Loeb's lasting contribution may be this: a challenge to scientific dogma and a reminder that openness to the unknown is essential to discovery. Umuam now drifts silently through interstellar space, its secrets still intact. But the conversation it sparked about alien life, scientific courage, and the nature of curiosity continues, and perhaps in the end that is the most important message it delivered. The proposal that Umuam might be alien technology captured headlines and public imagination, but it was met with firm skepticism within the scientific community. While no one truly believed the object was ordinary, many experts felt that jumping to extraterrestrial origins skipped a crucial scientific step: the search for natural explanations. In science, even the strangest phenomena are first approached with the assumption that they arise from known physical processes, however unfamiliar those may be. One of the earliest counter-theories came from a team led by Darrell Seligman, then a postdoctoral researcher at Cornell University. He agreed that Umuam's trajectory and acceleration were perplexing, but instead of invoking artificial propulsion, he considered a subtler force outgassing. Typically, comets exhibit visible outgassing as they near the Sun, with water ice sublimating into gas and forming characteristic tails. But Seligman proposed that this object was composed not of water, but of something far more exotic: solid molecular hydrogen. According to his hypothesis, Umuam might have been a hydrogen iceberg, forged in the ultra-cold depths of a giant molecular cloud far from any star. When exposed to sunlight, this frozen hydrogen would sublimate, releasing gas that would be invisible to Earth-based telescopes. This could explain the observed acceleration without requiring alien engineering, just an extraordinary but natural composition. At first, the idea seemed plausible. After all, hydrogen is the most abundant element in the universe, and under the right conditions it can indeed freeze, but doubts quickly emerged. Hydrogen ice, it turns out, is incredibly delicate. Even in the emptiness of interstellar space, it is vulnerable to the faint glow of starlight and the cosmic background radiation which would erode it over time. A block of frozen hydrogen simply wouldn't survive the vast journey to our solar system, and even if it did, its rarity made the theory feel like a stretch. Umuam appeared pristine, untouched by time or interstellar erosion, hardly the profile of a fragile hydrogen relic. As that theory faded, others stepped forward. Some researchers speculated that Umuam could be a sliver of nitrogen ice, sheared off the surface of a distant, Pluto-like exoplanet. Others suggested it might consist of exotic ices like carbon monoxide or methane, which could sublimate without leaving visible traces. Each theory addressed certain aspects of the mystery, but none offered a complete picture. There were always inconsistencies, unexplained anomalies, or physical constraints that pulled the solutions apart at the seams. Then came a simpler idea. Jennifer Bergner, an assistant professor at UC Berkeley, collaborated with Seligman on a new proposal. Maybe Umuam wasn't made of bizarre or rare substances. Maybe it was composed of regular water ice, just ice that had spent eons drifting through space, bombarded by cosmic radiation. In controlled experiments, scientists have observed that high-energy particles can become trapped within ice, forming pockets of hydrogen gas. When this irradiated ice warms up, such as during a close pass by a star, it releases the gas slowly, without a flashy tail or visible activity. Bergner and Seligman suggested that this quiet venting could account for Umuam's subtle acceleration. No alien craft, no exotic materials, just a natural object shaped by time and radiation, gently nudged along its path by invisible forces. They called it a dark comet, an object that behaves like a comet but conceals its activity from view. The theory resonated with many astronomers. It matched observed data, leaned on known physics, and avoided unnecessary assumptions. In the messy, uncertain business of interpreting deep space phenomena, it offered a grounded, satisfying narrative, yet not everyone was convinced. Avi Loeb, who first raised the possibility of a technological origin, continued to challenge these theories. He argued that even the dark comet hypothesis failed to fully explain the object's observed characteristics, its peculiar shape, its reflectivity and other unusual traits. More fundamentally, he cautioned against the scientific habit of stretching natural models to fit every anomaly. To Loeb, the universe is inherently surprising, and sometimes the correct explanation is the one that dares to embrace that surprise, even if it challenges what we think we know. While researchers continued to debate what exactly had passed through the solar system, one thing remained certain. Umuam had left behind more questions than answers. But in doing so, it also sparked a renewed willingness to look both outward and inward, to challenge assumptions, and to entertain the unexpected, whether from alien stars or within the physics of ice. A new perspective began to emerge. Perhaps the search for strange cosmic phenomena didn't require reaching far beyond the solar system. The possibility arose that the clues might already be nearby, hidden in plain sight. The question was simple yet profound. If an object like Umuam, silent, invisible to most instruments and accelerating without apparent cause, could exist in interstellar space, why couldn't similar bodies exist within the bounds of our own solar system? This line of thought redirected scientific attention inward. Researchers like Darrell Seligman began to closely examine the expanding database of near-Earth asteroids, thousands of small celestial bodies. Most of them largely ignored, orbiting between Earth and Mars. Traditionally viewed as inert remnants from the solar system's turbulent youth, these objects were assumed to be little more than cosmic debris. But what if some weren't as lifeless as previously thought? Scientists began meticulously analyzing years of observational data, searching for subtle anomalies, small, unexplained shifts in asteroid trajectories that couldn't be attributed to gravity alone. There were no dazzling flares or dramatic encounters, just faint deviations buried in long-term telescope records. Yet those deviations were real. They identified 6 small asteroids, all relatively near Earth, each exhibiting signs of non-gravitational acceleration. These weren't the kinds of forces that would fling an object across space, but they were significant enough to suggest some internal mechanism at work. Unlike traditional comets, these bodies lacked visible activity. No tails, no gas jets, no glowing halos. On the surface, they appeared to be ordinary asteroids, rough, rocky and unremarkable. But their movement hinted at something more. The behavior aligned with the dark comet hypothesis. Objects that don't erupt with obvious outgassing, but instead release faint streams of invisible gases like hydrogen through tiny fractures or thermal processes. It's a subtle phenomenon, enough to alter an orbit ever so slightly, but too weak to catch the eye. Among the 6 anomalies, one object stood out. 1998 KY26. A diminutive asteroid just 30 meters across, smaller than a soccer field, yet rotating at a blistering pace, completing a full spin every 10 minutes. What made it even more compelling was its upcoming encounter with a visitor from Earth. The Japanese space agency JAXA had already planned a flyby of KY26 using the Hayabusa 2 spacecraft, which had recently concluded its landmark mission to asteroid Ryugu. Initially conceived as a reconnaissance mission to aid future exploration efforts, this encounter suddenly carried greater weight. If KY26 showed any signs of hidden gas release, however faint, it could serve as direct evidence of a dark comet, potentially reshaping our understanding of small bodies in the solar system. Even if no such behavior was detected, the mission promised invaluable insights into the quiet companions orbiting nearby, remnants of the past, or perhaps indicators of something more enigmatic unfolding in the present. Despite the excitement, the challenges remained formidable. Detecting minuscule emissions of hydrogen from a tiny spinning object millions of kilometers away is a daunting task. Yet, for the first time, there is a real opportunity to observe something that may resemble Umuam up close. Not just through models and distant glimpses, but through a direct encounter. This moment serves as a humbling reminder. Not all cosmic mysteries are distant or unreachable. Sometimes the universe leaves its riddles close to home, hidden among the quiet rocks drifting in Earth's neighborhood, waiting for someone to notice the way they move. If dark comets are real, and if a hidden population of them exists within the solar system, then the object that passed by in 2017 might not have been a lone visitor. It may have been the first of many, a subtle signal that something far stranger is much closer than once imagined. For a time, the object known as Umuam seemed like a cosmic anomaly, a once-in-a-lifetime interstellar guest whose fleeting appearance raised more questions than answers. Its strange trajectory and baffling characteristics made it feel like an isolated event, the kind of astronomical oddity that might not repeat itself for centuries. But in August 2019, the universe offered a second revelation. A new object was spotted streaking through the sky by Crimean astronomer Gennady Borisov. Unlike Umuam, which had defied classification with its silence and lack of a visible tail, this newcomer, eventually named 2I/Borisov, acted in ways scientists found far more familiar. It sported a bright coma, a glowing halo of gas and dust, and as it neared the sun, it unfurled a long, luminous tail, hallmarks of the icy comets born within the solar system. There was no ambiguity this time. Borisov was undeniably a comet, but it was no less extraordinary for its transparency. The size of its coma stretched across tens of thousands of kilometers, dwarfing many known comets, and its chemistry hinted at a different origin. High concentrations of carbon monoxide pointed to a birthplace in an environment far colder than any region found near the Sun. Despite being interstellar in origin, Borisov's behavior brought a measure of comfort to astronomers. It was foreign, yes, but it played by the rules. This familiarity stood in sharp contrast to Umuam, which had arrived unannounced, tailless and uncooperative, accelerating in a way no ordinary object should. The differences between the two couldn't have been more dramatic. Where Borisov conformed, Umuam defied. Yet both shared the same origin, deep space beyond the influence of the Sun. Together they shattered the long-held belief that interstellar visitors were exceedingly rare. In fact, astronomers have long suspected that the solar system is not an isolated bubble, but part of a bustling galactic network. Many foreign bodies may pass through unnoticed, too dim or too small to be caught by existing telescopes. Certain comets and asteroids, like Comet Machholz 1 or Hyakutake, display unusual chemical makeups that don't match any local profiles. These celestial interlopers suggest a broader truth. The solar system exists not as a sealed vault, but as an open port, a gravitational crossroads where materials from distant stars can briefly or permanently reside. And yet, among all these discoveries, Umuamua still stands apart. Its strangeness was not just in its journey, but in its refusal to conform. In many ways, Umuamua serves as a humbling reminder. The cosmos doesn't exist to validate human theories. Sometimes it delivers puzzles that refuse resolution. Uncovering the nature of something unusual is one thing. Uncovering its origin is an entirely deeper challenge. When the object later known as Umuamua was confirmed to be interstellar in origin, astronomers quickly began the search for its cosmic birthplace. The idea was simple in theory. If its trajectory could be traced backward through space and time, perhaps they could identify the star system it once came from. Initially, the task seemed within reach. Umuamua had entered the solar system from the general direction of the constellation Lyra. But space is not static, and neither are the stars. Everything in the Milky Way is in motion. As astronomers roll back the cosmic clock, adjusting for stellar motion, galactic rotation and gravitational perturbations, what once seemed like a promising lead began to unravel. By the time Umuamua would have passed through the region Vega currently occupies, Vega itself would have been nowhere near that location. Vega was ruled out. Attention then turned to other possibilities: nearby stellar associations, fast-moving groups of young stars, loose clusters travelling together through space. Researchers ran extensive simulations, hoping to find a match between Umuamua's speed, angle of approach, and some known stellar movement. A few candidate regions emerged, but none could be confirmed. Whatever system it came from, Umuamua had long since lost its origin to time. After hundreds of millions of years drifting between stars, cosmic radiation had stripped away any identifying features. Its encounter with our Sun was a brief accidental flyby. Now it's speeding away at 26 kilometers per second, heading toward the constellation Pegasus. With no spacecraft sent in pursuit, everything we'll ever know about Umuamua comes from the fleeting observations made in 2017. There will be no second chance, no full explanation, only mystery. And that's what makes it so profound. Umuamua wasn't just a rock. It was a fragment of another world, a silent visitor from beyond. Just weeks after its discovery, Umuamua slipped beyond reach, growing dimmer and vanishing from view by the end of 2017. Travelling over 26 kilometers per second and accelerating, it was untouchable by current spacecraft. Still, scientists launched Project Lyra, not a thought experiment, but a serious plan to chase it down. The mission would rely on gravitational assists, launching a probe toward Jupiter, then using the Sun's gravity for a powerful slingshot maneuver. Done precisely, this could boost the craft to over 70 kilometers per second, fast enough to catch Umuamua even decades later. But the challenges are immense. Extreme heat near the Sun, razor-thin timing, and the difficulty of finding a small, fast-moving object lost in interstellar space. Alternative plans suggest using planetary flybys to reach it more safely, aiming for a possible rendezvous by 2048. Yet even if successful, there's no guarantee anything remains to study. Some scientists argue it's better to look forward, preparing to intercept the next visitor rather than chasing a vanishing mystery. Still, for those behind Project Lyra, the pursuit is about more than data. It's a bold expression of human curiosity and the refusal to let profound questions go unanswered. Since Umuamua's surprise visit in 2017, astronomers have shifted focus from studying what just passed to preparing for what's next. New models suggest interstellar objects may pass through our solar system daily, though most remain undetected. That may soon change. The Vera C. Rubin Observatory, nearly complete in Chile, will scan the entire night sky repeatedly, detecting even the briefest flickers. It could reveal dozens of interstellar visitors each year, many slow and large enough to allow advance notice and potentially interception. ESA's upcoming Comet interceptor mission embodies this strategy. A probe that waits in space, ready to meet the next anomaly wherever it comes from. It reflects a new understanding that space is far busier than once believed. Still, not every visitor will be easy to catch. Some will slip by undetected, but others may offer close-up study, helping unlock secrets about our galaxy and the nature of these cosmic messengers. Umuamua wasn't just a mystery, it was a disruption. It defied expectations, sparked debate, and forced scientists to confront the limits of current understanding. Was it natural or artificial? We still don't know, but more important than answers were the questions it sparked and the wonder it reignited. Though fleeting, Umuamua left a lasting mark. It reminded us that even in a sky we think we know, something unknown may appear at any moment. It challenged our readiness and our imagination. Next time we may be prepared, eyes wide open, waiting for what dares to pass. To this day, no theory fully accounts for all of Umuamua's properties. The encounter was brief, the data minimal, the conclusions elusive. But the questions it left behind echo still. Was it just a strange natural object, a relic from a distant system, or something more? And did humanity in that brief silent moment witness the arrival and departure of something far beyond its current understanding? If you found this journey into the unknown as fascinating as we did, don't forget to like, share and subscribe for more deep dives into the mysteries of space and science. There's still so much we haven't discovered, and together we're just getting started.